machine learning, as well as your data processing, as well as your statistics and some math behind it. So if you're interested, please do sign up for the other sessions because we would be having this thing, which is our plan for this semester. So first of all, this is like one of our official first lessons, which is your computer vision. And also on the second day, which is tomorrow, you have this thing called Intro to Natural Language Processing. So if you have a look here, those on the those stuff that are highlighted in green are under what they call your computer vision track, which is like how to get computers to detect stuff easily and also like to interpret what stuff they are. While those in the blue track are actually those technologies behind ChatGPT, where they actually interpret language and you guys get to make like language models and chatbots. So if you're interested in either one of those tracks or perhaps both, you're more than welcome to come on both days or either one of the days if it interests you. And furthermore, we also have say in these like yellow weeks, if you decide to have your own project that you would like to experiment on your own, you can feel free to consult us, the academics team. We are more than happy to help you with your own personal projects regarding to like computer vision or like natural language processing. Okay, so with that said, and finally towards the end of week 11 and week 13, because we know that some of you are like year ones. How many of you here are year ones? Wait, one. How many of you are year twos? Okay, and the rest I assume is year three, year fours. Okay, cool. So because in triple E, I think in year one, year two, you have to take this module called IE 5, which is Intro to AI. And we felt that as part of like MLDA, it would be a good initiative to help you guys like master the core fundamentals of this module as part of our teaching process. So, oh, Mike. Oh, oops. Not loud enough.
Yeah.
I just click here. Mic check. Mic check. Mic check. Okay, it's clear. Is everyone online can hear? Okay, thank you very much. Right. Oh yeah, I see those like, green ticks there. All right, so moving on. So basically today we're going to talk about OpenCV. So for most of your computer vision models, it all boils down to OpenCV because OpenCV is basically the foundation of most modern day computer vision models. So what actually is OpenCV? So as you can see here, OpenCV is basically a real-time optimized computer vision library, which provides you tools for like manipulating images, for example, like cropping images or like highlighting regions of interest. Also, you can like manipulate colors. So as you can see, I guess you can look from the images yourself. First of all, for example, if you detect a face like has basically the whole facial region, but we do not want extra information such as the background. So what we can do is we can crop the image such that it only like includes the face, and so we can replace the background with like black color like pixels. So we just totally remove all information about the background, which makes it easier and faster to process. Okay. So moving on, we can also talk about like separating color channels. We'll talk about later. So for us humans, we view stuff in like normal light, natural light. However, sometimes some computer processing algorithms, they would prefer different color schemes, and also it makes it more efficient to process images. And hence, based on which model you're using, you might want to prefer to change the color from natural light to like perhaps like black and white or other variants of the color scheme. And finally, we can also talk about highlighting regions of interest, where, for example, we're going to detect an expression. So let's look at the face does not give you enough information. To detect expressions, you will need to look at the eyes, the nose, and also like the mouth, for example, like whether it's happy or is it sad. So, and the special thing about OpenCV is that because it's such a like big library, it allows us to like process like large amounts of images all at once, and also it gives us a lot of like control over what do we want to do with the images. computers because that's all the built-in functions that someone else has already written for us. So far so good, I assume. Oh, and the best part is open source. So it's like totally free to use forever. Okay, so we'll go into like the actual code later on. So for the first half an hour, we're talking about like the theory of computer vision. So moving on. First things first, we talk about your natural color and what does it mean for computers to like store images. So how many of you have heard of RGB? Can I have a show of hands? Okay, 1, 2, 3, 4, 5. Okay, almost everyone. That's cool. Right. So basically in computers, RGB is represented as like numbers because computers by themselves, they have no idea what red is, what green is, what blue is. So the idea is to them it's just an intensity value, a certain wavelength of light. So however, there must be a way to store the information, right? So what we can do is we can split the channel into 3 channels, red, green, and blue. And also we can represent the intensity of red by the intensity of like the value here. So from 0 to 1, right? 0 being darkest, 1 being brightest, we can represent, say, red from a scale of 0 to 1. So one example is, have a look at the feathers. The feathers are red, and they are represented most heavily in like the red channel, while, for example, the wingtips and like the tail is blue. They're represented the most in the blue channel. For example, you can notice that the blue channel here is like especially bright at the tail and the wingtip portions. And one more like example would be the LEDs, which will be, for example, the RGB LEDs would display differently depending on which channel are you looking at. So red, in the red channel, you'll notice that the red LED is the most lit up, while in the green channel, the green LED is the most lit up, while in the blue channel, well, as the saying goes, the blue lights up. However, you might be wondering, why why the other LEDs are lighting up? For example, red, right? Why is the blue LEDs lighting up? Anyone want to take a guess? Like, why is the other LEDs still lighting up? Anyone? Okay, perhaps user in a yellow shirt. Any guesses? Correct. So you mentioned something about combining the colors together, right? So in fact, like different colors have like different combinations of RGB. For example, right, say like bright red and dark red. So like dark red, right, maybe has like only like a small amount of red, but for example, bright red, you need more green and more blue. Because if you think about it, when you add RG and B, right, all together, it becomes white. And if you remove RG and B, totally zero, it becomes black. So like the brighter a color is, the more portions of like the other colors they have. Like, I hope that makes sense. Because now we shall go over to the code a bit and we'll demonstrate it to you like what it actually means for RGB to be represented in code. So if you pause a moment, and now, okay, we'll be giving you guys some time, run this code later. This is just like we'll give you guys some hands-on time in the second half. But first of all, I'd like to demonstrate what RGB actually means. So as you can see here we are filtering out blue, right? So as we filter out blue, this is the top part. We filter out the Test. Can? Okay, wait. Share screen. Testing. Okay. Testing. Can? Okay. Wait. Are you allowed to like accept new participants? Okay. Can. Right. I'll continue. Sorry for technical difficulties, but okay. So in terms of the code, right? So I hope that you all can like see like why some of the blue is still there and some of the blue is like missing. Okay. So far so good. Right. So let's go back to like computer vision. So in terms of notice how values here, but the brighter the value, wait, testing. Okay, I'll stand you. Testing, testing. Okay. All right. So if you all can see, have a look here. So basically, like the value here, right? 0.674 is like a higher value compared to like say 0.3. So in that case, the blue will be much brighter than this blue. So up to this point, anyone has any questions? No? Okay. Right. So let's move on. Okay. So first of all, like does anyone know who this is? Like who this football player is? I assume you all know. Messi? Come on. Right. So anyway, the thing about why I chose this particular picture is because that in this picture he's wearing his Barcelona t-shirt. However, you notice that on the left-hand side, the colors seem to be like reversed. So one thing to note is that OpenCV, for some weird historical reason, they use BGR, which is blue, green, red, instead of RGB, which is red, green, blue. So if you notice, on the right-hand side is the original image, which is RGB. But then for some reason, if you switch it to BGR, it swaps. So notice how the red and like blue stripes get swapped. But then in that case, well, the white and the black do not get swapped. Does anyone want to take a guess? Perhaps user with anti t-shirt? Yeah. Why does the white and black not get swapped, but the blue and red get swapped? Correct. So that is actually the answer. So reason why is like black is like 000. So when you swap the blue zero and the red zero, it does not make a difference. Same thing with the white. If like white is like red one, green one, and blue one, if you swap blue and red, it does not make a difference. So, however, one thing to note is that some stuff, like for example, the human skin, right, is naturally slightly reddish. So when you swap it over to blue, right, you notice that his face looks a bit blue. So that's basically the small like caveat that you have to like take note of when you use OpenCV. Okay. So finally, one more theory part before we go on to code. So first of all, is this thing called grayscaling. So sometimes, right, the color of an image does not matter. So, for example, sometimes you want to see how bright something is. For example, like you want to take photos of like the moon, for example. Like the moon is just gray, like you don't really care like what colors. So to make processing faster, right? To make your computer like visualize the thing faster, you can throw away the color information. So what most people do is they can merge all three RGB values, like red plus green plus blue. And you take the average, you divide by three, and you get what is called a grayscale value, which is the average. So one example is, for example, you see the rows right at the top right corner. It's like it looks very distinct in the color image. It's like pink and sunny like background. But if you look at the grayscale image, notice that the same petal of the rows just blends in like naturally into the background. So we can say that the brightness values of those 2 points are actually similar when you actually do the math. However, like there's definitely other like more complicated ways of grayscaling because this one is the most primitive way. You add red, green, and blue, and you divide by three. However, like some scientists have discovered that we detect green color a bit more intensely. So depending on that, you can just give more weightage to the green color, like add like double the green if you want. But that's like more complicated, and there should be a function in OpenCV for that. So if that's it, we have completed the first part of the theory, and now we'll go on to the code. So, can I just check if everyone has managed to receive the code file? Yes, no? Can I have show of hands? Code file? Yes, yes. All right, cool. So first of all, I would like you guys to just open up this thing called Google Colab. So it's just Google Colab. Oh yeah, so yeah, no worries. If you guys have a bit of time because it's a bit it takes a while to set up. So all of you just go to Google Colab, sign into your Google account, and open up the code file that we sent you. For those online, are you guys let me check? Oh yes, CR7, Ronaldo. Wait, it's not Ronaldo, right? Messi, right? Yeah, yeah, yeah. Wait. Okay, so I'll just give you guys some time. Open up Google Colab. So once you're in Google Colab, right, you should see something like this. Okay, so I assume like everyone has like opened it up. If those online facing any difficulties, feel free to like enter the chat. Our technical support staff will be promptly helping you. Right, so first of all, we would like to test your system that see if we can upload an image. So what I would like you to do is, I'd like you to just like download any random image. So basically it's like, first of all, you run this cell. Press play first. First step, press play. It will prompt you to like connect to your Google Drive. So just wait a bit, press play. Okay, it's loading. All right, still loading. Yes, so it definitely asks you to like ask, do you allow it to connect to your Google Drive? Say yes, connect. And for example, I'll just connect using this one. Just press continue, just accept it all the way. Continue. Okay. And if everything goes to plan, right, you should see a green tick here eventually. So those online, if you have any difficulties, you can let us know. Those same goes for those here present physically. Right. Does everyone see a green tick here? 35 seconds. Okay. Okay. And that table. Can. Right. That table over there. Can. Okay. I assume everyone's okay. So now, first things first. I'll just teach you guys to like navigate your file tree. So this is your like workspace. And what happens is basically, uh, on your left, you have this thing called your like your file system. It looks like a folder. I would like you guys to press on this folder. So it's files. It's on the left hand side. Files, files. Okay. So first things first, I'd like you to go out, basically up one level. So basically now you're in the main parent folder. So for those who couldn't catch along, you press files again. You were just now somewhere inside. I would like you to go up one level to like the outermost level. So for example, if you're inside here, yeah, just go up one level. Yeah, there should be the folder called dot dot. Right. Everyone managed to do it? Can? Can? Okay. Right. So moving on. Now, first things first, let's just import like some random picture. Let's say let me import, let's say cube. Okay, let's say robot. Okay, wait, never mind. Let me just check the wait, sorry. Wait, wait, wait. Okay, so one of the ways to upload, right, is either you can go to your like how to say your folders, and from here, right, you can either drag and drop. So for example, let's go like say downloads. Let's just go to yeah. For example, I've downloaded this thing called image.jpg. So for you, you can just go onto Google and download anything. But I'll just show you the process of uploading first. So if everyone can just have like about 1 minute of attention. So what you do is you go to your downloaded picture, you take this picture, right? Drag it inside here. You automatically drop and upload. Then of course you'll say like warning, so on. Press OK. And tada, your image should be right down here. So I'll give you guys about like 3 minutes or something, find a like cool image and just like download it and repeat the same steps of dragging it down here such that you have the image in your file folder. And make sure your image is like in the outermost folder and not like inside one of the subfolders. So yeah, for those online, okay, no worries. Right, so for those online, I'll repeat the same process. So in case of anyone, okay, so first of all, I'll download a random image. You can like preferably rename it to something like say ABC or like 123.jpg, which is easier to type. Then what you do is you will drag this thing into your file system and make sure your file system, notice the left-hand side folder. If you cannot see this, make sure that you have already exited to the main folder by clicking this thing. It should be up here. But yeah, for those online, can you guys follow along? I'll give you guys about 5 minutes. Yeah, you can just pick any image you want. Oh, good question. Actually, doesn't really matter, JPEG or PNG, but preferably JPEG for this one. Like, but honestly, it doesn't really matter. We'll talk about the differences between JPEG and PNG slightly later. But yeah, for now, it's JPEG. Okay, I assume everyone can upload. Okay, so assuming everyone can upload, uh, anyone still uploading? Just raise your hand. I'll pause a bit. Okay, yeah, I'll give you guys about 2 minutes. Anyone any help uploading? Anyone still uploading? You need any help? No worries, no worries, no worries. Online? Anyone still uploading? If anyone's still uploading, can just like say something in the chat. I'll wait a bit longer. Okay, I assume not. So let's move on. So that's it. After running the first part, like importing the Google Drive, like adding an image.jpg into your folder. Now, first things first, you need to import computer vision, which is OpenCV. So here's a bit like a very like weird historical fact. The thing is, it's called OpenCV, right? The thing is, when you download it, it's called OpenCV Python. But then when you import it, it's called CV2. Like, don't ask me why the two is there, but it's just historical reasons. So with that said, just press play, which is equivalent to run. So what you're doing is you're just importing like all the libraries that you, like your NumPy, your like plotting device to like plot the images, and also your OpenCV. Okay, I assume that everyone has a green check mark here. And then now, first thing you get to the fun part. First of all, I would like to just this code first. If all of you would follow along, you can press the play. And ideally, your image should show up here. If there is some error, right, then I'll come over in a bit. But basically, your image should show up here. Just press run first. Anyone's image not showing up? Yeah, just raise your hands. I'll come over. Online as well. Online, if anyone's image not showing up after you press run, you can feel free to time and just so, one more thing to take note, right, is that basically the imread, notice how like your code here, right, as the name of the image. So you must also make sure that this wording matches the name of the image. So for example, if you name it ABC, right? So let's just say I right click. Let's say I rename the file to ABC. Oops. Yep. Wait, one sec. Let's say I rename it to ABC. I need to ensure Wait, wait, what? Yeah. I need to make sure that everything here is renamed to ABC. Yeah, same thing if you're using a PNG or like JPEG file, make sure that the naming is consistent and you should be able to see it now. So anyone else has any issues with the image? Can try again. Those online, any issues? Those physical, any issues? All right. One sec. Line, anyone facing any difficulties? Okay, hide. Okay, so in the meantime, explain what the code actually does. So first of all, what we're actually doing here, let me just make it slightly bigger for those physically present. So what we're actually doing is, first things first, this command loads an image. So basically, calling OpenCV to read an image that is named ABC. And then this line, CV2 imshow, basically stands for image show. So it shows the image and it displays it. So for example, my original image was this RGB cube. When I run image show, it shows me the original image. Okay? So second line is basically your convert color. So CVT color stands for convert color. It converts an image from color, and notice is BGR and this thing to gray. So it's essentially converting into grayscale. And finally, we're going to show it again. So CV2 im show, same thing. Therefore, this thing is in grayscale. Now, if you notice, the blue, red, and green, right, in the grayscale image, they look exactly the same because they have the same intensity, right? Even though they're different colors, but they look like more or less the same. Now, finally, you talk about getting the blue channel, the green channel, and the red channel by splitting it up. So notice how we have 0, 1, 2 here. So in programming, how many of you have programmed before, like Python? Most of you? Right, so you know that 0 is the first one, 1 is the second one, 2 is the third one, right? So in that case, B is the first one, G is the second one, and R is the third one. And hence, we can display the colors in order. So R, G, and so that said, notice that how in R, the bottom color, the bottom left corner is the brightest in accordance with our image. And for G, the top right corner is the brightest. And for B, the top part is the brightest. So for your own image, right, I would assume that your image has like some like, I guess some like variation in color. So I'd like you to just like take a note, like take a notice about where exactly in your image has the greatest like red, green, or blue concentration. So yeah, anyone has anyone has still any problems with that image? Okay, you want sec? By the way, online, for those online, if you all can follow along, or if you all cannot follow along, just let us know in the chat, and our technical staff will come to you. I think that you guys are still like comfortable in the colors. Those online and issues. Okay, those are the back physically present and issues. Can yeah. So if you all want, you can just try and mix and matching like different images. Like you can search for like a rainbow, for example, and just like copy and paste the rainbow inside there. See what's the difference. Okay, but with that said, uh, wait, that's it. Wait. Yeah, the image, how like runtime and yeah. Okay, so with that said, for those like who have done the first part, let's move on to the second part, which is your weird RGB thingy that we talked about. So I would like to first of all mention that make sure that the image name here is the same as the image name in the file. So basically make sure it's consistent. If you name it ABC, please rename it here ABC as well. So first things first, we would like to convert an image from like BGR back to RGB. So because of how like OpenCV works, this is how it is. So OpenCV reads it in as BGR, but Python reads it as RGB. So in that case, we just like have to add a minor inconvenience here. And now moving on, let's just try to start filtering out the colors. So remember just now that we mentioned that you mentioned that the range of values is from 0 to 1. However, in computers, right, representing decimals is very hard. So what we do is we represent numbers from 0 to 255. Some of you might have heard like 256, 256, 256. So in this case, we use 0 to 255. So if that's it, we are trying to limit, what we're trying to do here, right, is trying to limit the amount of blue. So as if you all can remember, the first number is always your red. So for red, right, the range is from 0 to 255. For green, the range is from 0 to 255. But for blue, right, we will be slightly restricting the range. So from 0 to 250 and so on. So for example, if you notice that when you want to filter out a moderate amount of blue, we will filter it from 0 to 200. Oh, wait one sec. There's someone online. Uh, 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 wait 1 second. Okay, so anyway, 1 sec. By the way, for those online, like in the future, like if there's any like future questions, just feel free to like type in the general chat because like our technical team is like a bit off screen. They are doing the hard work of like maintaining everything online and also helping you guys debug. Okay, so anyway, let's move on. By the way, so speaking of which, this is the bottom array. So notice how we filter it from 0250, 0 to 200. And now, if you want to filter out a lot of blue, it's from 0 to 30. And if you want to totally filter out blue, it's from 0 to 0. So the rest of these things are just your extra steps. We'll explain it later. But basically, if you notice how like at the very start, we start filtering out blue, and there's more blue gone, and there's even more blue gone, and so on. All right. So I'll give you guys like a bit of time to play with the values. If you all want, you all can just, instead of changing blue, right, try to change like red or try to change the green, for example. And if you really want and you're very adventurous, you can feel free to change the zeros to a higher value. It's up to you. So as long as you just experiment with values and just see how it affects the final image. And don't forget to press play in the end to run it. 1 second. Oh, right. I didn't rename my image. ABC. There we go. Should run. Yep. So I'll give you guys like 5 minutes to play around with the values. Yeah, feel free to experiment. You all can also experiment on your like own images if you want. For those online, any questions? Oops, 1 sec. Those, yeah, I'll give you guys like until like 7:45. Yes. All right, guys. So, if anyone's wondering, about the order of images, so the first image is it's a bit more advanced. But first of all, the subsequent images, right? On the left is the original image, and on the right is the modified image. So left original, right modified, left original, right modified. Okay, and for those of you wondering, right, what are all of these extra codes are? Basically, these codes are what you call your actual manipulation function. So when you want to like say manipulate an image, right, you have to filter out some values. Use a mask. So a mask basically only allows values that fall within a certain range to pass through. For example, here, right, we only allow like blue from 0 to 30. So anything that exceeds the 0 to 30 value of blue gets like masked away. Like basically it gets covered. So if you want to have a look, right, you can actually like copy this im show, like mask one. You can actually copy this thing to show your different masks. For example, mask two. And you can run it again, and it will show you in black and white which pixels get passed through. So as you can see here, this black and white. So a mask is basically a yes or no question, which actually asks, should we pass this pixel? Should we not pass this pixel? Does anyone have any questions? Yeah, you can just play around with it, experiment with different masks, and so on. So for example, right, let me just ask you guys a question. What if I were to put this thing, say to like, say 100, 100, and 100, and this one to be, say 255. Can anyone like guess? Perhaps, yes, perhaps you in that t-shirt. Yeah, so say if I put like 100 to 255, right? What am I filtering out? Or like what do I want to keep? The brighter values, the darker values, the red values. Okay, so let's say if I were to apply this thing, right? Let's say I change numbers. Because just now, right, it was like I changed only the blue value, right? Now if I change everything to like say R100 to 255, G100 to 255, and blue 100 to 255, what colors am I keeping? Like for example, what colors am I keeping? Like let's say I come to the cube here, right? What do you expect to be like left? Okay, that's one way to find out. So let's just try experiment with it. Only one way to find out. So you can experiment with it and notice that after I filter out the lower values, right? The 100 to Wi-Fi are like actually the higher values, and hence only the brighter values should be kept. So and vice versa. So it's a very good idea to just like play around with the values. But I assume that all of you have tried so. Now we shall move on. Okay. We shall move on to the more theoretical part and like the back to the theoretical part, back to the more advanced image processing techniques. So now I will pass the time to like Aditya, and yeah, y'all can feel free to just mess around with this code. Like I think we'll give you guys a bit of time at the end. But yes, now I'll pass the time to Aditya. That's right. Come. So okay, the tabs here. So you know how to use, right? This is a tab. So then the vertical tabs, then see. Can. All right. So
Yeah, can I get the mic?
right. I think this mic does not work. You need to speak.
It's just for aesthetic purposes. Okay, so good evening, guys. Now I'm Aditya, and I'm one part of the MLDA CADS subcommittee as well. So I'll be taking over the workshop from now on. So now let's introduce you guys to some common pre-processing techniques, commonly referred to, in this case, commonly referred to as image morphology. And we will be looking into two particular operations, dilation and erosion. So, like the name suggests, erosion is to chip off some features in an image that you may consider as not essential, whereas dilation is to take a feature and then overinflate it. So that basically sums up the key operation of these two. So now let's take two examples here. So you can see two separated features in this image. So basically, an image is just a two-dimensional array, right? So you can consider all black objects as 0 and white objects as 1. So upon performing dilation, we are basically inflating both the features. So if you notice the blob here, it has expanded a bit, and this one as well, and thereby both of them have essentially fused together. And if you look at the second one, the same image, and if we perform erosion here, each of the features has become chipped off in a way. Okay, so that uh, basically sums up what dilation and erosion is. So should we like explain the mathematics behind it, or okay? Sorry. Yeah. Okay. So where's the camera? Okay. So now let's take a 5 by 5 matrix. 0, 0. And we can assume this as the image. And so in when it comes to dilation erosion, there is another essential element called the kernel. So this is a smaller version of the image, a smaller two-dimensional matrix, and we in this case we will take it to be a three-dimensional matrix. So this. Okay, so this is the kernel. Now, what basically happens in erosion and dilation is we take this three-dimensional matrix, and particularly the center of it, and we place it on each pixel of the image, and we move around each of the pixels. So while in doing so, while dilation, we will consider, let's take one particular pixel, and in that instance, if all the ones overlap with ones, then we can replace that pixel in the image with a 1. So now let's perform an example. So if we take this matrix and if we place it here, it will be 1, 1, 1, 1, 1, 0, 0, 0, 0. So as you can see here, all the ones in the kernel does not coincide with ones in the image. So this 0 stays a 0. And if we consider the case with all the boundary zeros, it will form the same pattern. So in the case of erosion, all the boundary zeros will remain a 0. Now, if we consider 1, so let's take that case. Okay. So now let's take the case where we place a 1 here. And we notice that in this case as well, there are 2 pixels where 1 does not coincide with a 1. So we replace all the middle ones with zeros as well. Now, there is still one case remaining where the center pixel hasn't been tested yet. So in that case, if we do end up performing that, so here we notice that all the ones in the kernel have overlap with ones in the image. So this is the only pixel that matches the criteria for erosion. So in that case, it will have 1. So by the definition of erosion, it essentially just chipped off all the surrounding ones, and we are left with only one pixel of one. So that summarizes what erosion is. Now, when we look at the process of dilation, it's the exact opposite of it. So in this case, instead of restricting it by saying all ones need to overlap in order to produce a one, we are minimizing the criteria to even even if one particular pixel in the kernel matches with the one in the image, then we consider it as a one. So if we consider the case of the surrounding zeros yet again, it will have 1, 1, 1, 1, 0, 0, 0, and 0. We can see that even in this case, it does not satisfy. There isn't a single one in the kernel that overlaps with the one in the image. So the surrounding zeros still continue to be 0. Now, okay, no, not all the surrounding zeros. Sorry, there are some zeros here that do satisfy the criteria. My bad, sorry about that. Okay, so now let's take a particular class of the surrounding zeros, in this case, something like this. And if we end up placing the kernel there, we see that there is one pixel in the image that satisfies the criteria. So we can replace this with 1. And considering that if we end up placing the kernel in any one of these, it's bound to satisfy the criteria of at least one pixel overlapping. And that leads to all of the 3x3 internal matrix to be filled with 1. So yeah, as you can see here, the small square of ones has been inflated, and pretty much all of the image comprises of 1 here. So that summarizes erosion and dilation, and it's a very essential pre-processing technique to chip away some of the not essential features. So one particular example could be that I could give from my own personal experience is from my research in Eureka. So what I do is I use CNNs to detect cells that are infected by cancers. Basically what the detection looks like is take two particular cells and the CNN just marks it with a bright yellow circle. So that's how the detection looks like. But in certain cases, when the cells are too closely present, then the detection might sometimes, both of them are considered the same cell. So in such cases, we can see a morph kind of circular blob. So what we do is we perform erosion, and in such cases, the center fusion region is just chipped away, and we get a proper detection. So that's one particular application for erosion, and I'm pretty sure there are some for dilation as well if you look more. So moving on. Um, how do we go to the slide? Huh? Home, right?
Usually on my front.
Okay, perfect. Okay, so moving on. Now talking about convolution, quite similar to what we performed earlier, taking a small particular kernel, the 3x3 matrix that I was talking about, and moving it across each particular pixel in the image. So that is what convolution is. The process of convolution is quite similar as well. So in this case, as you can see, there is a small S matrix, which is the kernel, and this A matrix is the image. So what happens in convolution is you take the kernel, place it on each pixel, and wherever there are white color pixels, right? Essentially, they represent 1. So you multiply the ones and zeros with the pixels. So what that means is, so yeah. So suppose you take the image as 0, 0, 0, 0. Yeah. So if you take a 3 by 3 matrix, so let's consider this as the 3 by 3 matrix. So you take the center of the image, you put it here, and you transpose it across each of the pixels in the image. So in this case, what it will look like is 1, 1, 1, 1, 1, 1, 1, 1, 1. So what you will do here is you'll perform dot product of the two. So in this case, you will multiply 1 with 0 plus, and you'll sum it with 1 into 0, 1 into 0, and finally 1 into 1, which will result in 1. So upon performing convolution, you will get a 1 in this pixel. Similarly, you will get 1 here as well, and so on. So that's how you perform convolution operations. And it's commonly used to detect specific features, shapes of features. So if you look at the image here, yep. So if you look at the image here, I think this is from the video 3, yeah, the 3 blue one convolution. So we are taking the image of phi here, and you perform it using convolution using this normalized kernel. And what I mean by normalized is you're taking a 255, the maximum intensity of red, and you just limit it between, instead of having the range of 0 to 255, you're limiting it between 0 to 1. Minus. So that's this is, and you're taking it and you're performing a convolutional operation. And this is the resulting convoluted image. Yeah, as I was saying, convolution is common to detect specific features in the image. So one of the first use cases, one of the first applications of convolution is to detect horizontal and vertical features. So that's what is represented by the kernels here. These are specially designed kernels to detect vertical features in this case and horizontal features in this case. So as you can see here, this is a Sudoku image of a Sudoku example. And if you perform convolution using this particular matrix, you can see that all the vertical lines have been isolated and the horizontal lines have just disappeared. And quite similarly, when you perform convolution using this, all the horizontal lines exist while the vertical lines have disappeared. So that is how you isolate some specific features in the image. So how this works is that once you perform the convolution and you get something like this. Now let's take the example of the vertically convoluted image. And this is how the vertical edge looks like. So we take every point. So let's take one particular pixel A. And in this case, A has a higher intensity than the surrounding pixels, in this case, B and C. This is because we perform convolution and this is the brightest part of the image, whereas the rest of the pixels will just be black. So we can see that A intensity is the maximum. So we will take this particular pixel and add it to a particular array, saying this is one of the selected pixels that belong to the vertical features. Now, once that's done, we still need to perform one more operation called thresholding, so that we don't just take all pixels that resemble a vertical image. We need to be very sure that pixel that we are selecting is part of the vertical feature. So what we do is we set a minimum and maximum value. So what these are is just intensity values. It could be, so intensity ranges from 0 to 255. So commonly you can set this to 100 maybe, and a maximum of 255 of 200. So any pixel that surpasses the maximum threshold, we are sure that it's a vertical edge, and that will be added into the array of vertical edges. And if we take, then we consider another range, the range between the min val and the max val. And in this case, we consider if the pixels are attached to the pixel A, then we are sure that it's one of the vertically detected edge features. And whereas if it's part of some random edge uh, that's not connected to A or C, then we are pretty sure that it's not one of the vertical features and we just throw it in the dustbin. So yeah, that pretty much summarizes how the vertical features, horizontal features are detected. But convolution can be performed on any sort of features. You can detect circles, you can detect triangles, sharp edges, and so on. So that brings us to an basic introduction to convolutional neural networks. So convolutional neural networks use different kind of features that an image. So if you take a face of a person, there is uh, part which resembles an eye. And that horizontal part will also have small curves, which is also another feature. So all of these different features are what makes us and what makes the world that we see. And if we take enough of these features, we'll be able to construct something that resembles a face. So some specific sections of the face. And if you take those features, you'll be able to finally create some morphed images of sorts, which is what the convolutional neural networks are used to classify whether it's you or someone else. So that's how a computer, the convolutional neural network, is trained to on different classes of features. It's a commonly used algorithm for facial recognition and so on. Moving on. So yeah, we're not going to directly look at convolutional neural networks now, but we can look into some basic, readily available platforms to perform feature actions like facial recognition, gesture recognition, and so on. So one of the commonly available platforms is MediaPipe, and it's created by Google. And it's used for readily deploying these machine learning libraries for for usages like I mentioned before. So yeah, you can start accessing this link and try it out yourself. It's available, right, in the collab? Yeah, so you guys can go to the collab now. Okay, sorry. Media be part of the activity or? Mhm. Okay, so guys, before we move on to MediaPipe, just can I get your attention again, please? So this is when as we talked about erosion and dilation, right? So this is how it's implemented using OpenCV. So first, you take the image and you perform imread. So in doing so, you're storing the image's features into the variable image. And now you create a kernel using np.ones. This creates a 5 by 5 matrix comprising of all ones. And yeah, that pretty much summarizes the kernel and the image, which are the two matrices that was introduced in erosion and dilation. So for performing erosion, you just use the cv2.erode, and you will supply the image and the kernel. And the iteration here represents how many times the kernel passes through the image. So in this case, you're performing one iteration, which is just taking the kernel and then passing it along each of the pixel in the image. So if we do it two times, then we'll further take the kernel and do the erosion again. And if it's 10, we do it 10 times and so on. So yeah, in this case, you're just going to perform once. So that's how you do erosion. And following that, dilation is just replacing the function erode with dilate. And yeah, you can see that the original image is a triangle consisting of triangles inside. And yeah, performing dilate just expands the features, and you get a more dense kind of triangle. And following that, sparse just chips off all the surrounding pixels, and you get this barely visible triangle. Sorry? The kernel is the small matrix that I was talking about. So if you look at this one here, so this is the kernel. This is the image. Oh yeah, yeah. Are you talking on the code or? Oh yeah, code is. Yeah, it's a 5 by 5 one. All one. That is zero here. Okay, so you can try executing it and you will get something similar to this. And moving on, talking about edge detection. Now let's look at this. Wait, is this a .mp4? Okay, why is it not playing? Okay. Is it pre-run for them?
If you want, you can run the thing. I can show them on the spot.
Okay. You said you faced a problem, right?
Because the video is probably not really fast. On the video, this break rules.
Okay, seems like it's loading. Perfect. Okay, so I think it's just taking each frame of the. Okay, okay. Wow. Okay, so now let's focus on edge detection. The implementation is as follows. So in this case, he had passed a video instead of an image, but it's okay. Video is just passing multiple frames of images and viewing it at the same time. So that's why you're getting like thousands of images. So yeah, here you pass the video to cv2.video capture, and that stores the entire frames of all the images into the variable cap. So now you execute a while true, which is sort of like an infinite loop. And here you are reading the image and you're basically converting it from BGR to grayscale. So that's what is stored here as a grayscale image. That's why the colored image is turned into a black and white image. So upon doing that, you are finding the edges using cv2.canny. So here you're taking the grayscale image, you're setting a minimum threshold of 30. Remember the minimum intensity and the maximum intensity I was talking about? So in this case, the minimum intensity is 30, while the maximum intensity is 100. So anything above 100 is a perfectly detected edge, while anything in between requires it to satisfy some certain conditions. So now we have all the pixels, an array of pixels that are considered to be part of the edge. And basically, yeah, we take both of these images, horizontally stack them together, and we are just printing it out. So it will continue to run this loop until you press Q. So upon doing that, okay, so in this case, it's not like a infinite loop. So that's why you don't necessarily need to do that. So once everything is printed, you can see all the edges in the image being distinctly detected. So in this case, yep, all the edges are represented as white, while the surrounding features that are not part of the edges are just neglected and are stored as black pixels. Okay, so that sums up erosion, dilation, and edge detection. Now let's move on to media pipe. Where is media pipe? Media pipe.
So media pipe,
Yeah, where is it? So you want to do hand gesture? Can they run it? Okay. 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 So I was mentioning about MediaPipe, right? So MediaPipe is a platform offered by Google to deploy readily deployable machine learning libraries. So there are plenty of them. You can see there is object detection for detecting several already pre-trained model that detects almost anything that you show in front of it. So it's like dogs, cats. If you show a pen in front of it, there is a high probability that it will detect a pen. And yeah, there's image classification. There is hand landmark, which you can use to perform different hand signs and make it recognize stuff, and so on. There is quite a lot. You can just go to Media Pipe Studio and you can check out the different services offered by this platform. Now, yeah, you can scan this QR code and you will be able to access MLDA's GitHub repository that has already downloaded all the essential Python scripts for you, so you can try accessing it. Oh, okay. So you just want to do that? No Python? Okay. Okay. So that being said, how many of you guys have Python installed in your laptop? Okay, more important question. Who doesn't have Python installed in their laptop? Okay, that's pretty good. Then hopefully every single one of you should be able to run the media pipe scripts. So go to the QR code and you can access MLDA's GitHub repository and you can try testing out the codes yourself. Oh.
Yeah, for those online, same thing. If any issues, you all can feel free to type in the chat. Wait, I saw. Okay. Those online, any issues? Yeah, so the idea is right now, like we're going to get you guys to run the webcam-based code. So just to test your webcam if it works. So for those of you online, like who has like not programmed in Python before, y'all can feel free to just like go on the MediaPipe website and follow along. Or if you have experience in Python, you can try like running the webcam-based code just to test your webcam works. So 1 second, I'll send you guys a link for the online MediaPipe. Um, Git, yeah, you can either like Git install or like no, wait, how do you install Git itself?
In command.
There's
It'll
di
come installed, right?
there's different ways for like Mac and Windows, but worst comes to worst, other than just copy and paste like the traditional way, just copy and paste from GitHub.
Copy.
Like just copy the raw file.
Python environment, we configure your environment part. Yeah, I think it's very easy. Yeah. So so guys, if you have a few seconds, you can just look here for a demonstration. So this is just one of the codes that we got from the repository. So this is called hand landmark detection. So what it does is you can just point your finger in front of the camera and you can just track each of the fingers, its individual motion and so on. And it can also differentiate between the left and the right hands. So one of the possible uh, applications for this is maybe sign language. So you can train different machine learning models to identify different shapes of sign languages, and you can perform sign language to English translation and so on. So these are some particular ways in which you can use these readily available models. So I believe that you guys have a project coming up to do in MLDA. So yeah, you can consider exploring some of these models offered in MediaPipe and maybe even use some of them for your project. Yeah, you guys are free to explore the different kind of stuff. Question.
Maybe maybe you can hang on go to the second protocol yeah, because I think only 8:30. But then the people online is being left out. Right.
Hi guys. So for those online, right? These are like links to like the collab notebook, the revision quiz, and the feedback. So for those of you who like haven't actually like or those who have like done with like code or like would like to move on to something else, you can just have a look at the revision quiz. And also you can provide us some feedback. Yeah, please remember to fill in the feedback form on our performance and how the workshop is. But yeah, for those of you like both physical and online, y'all can continue like working on like the Python code, or y'all can just go on an interactive like chat, like the interactive like website that requires no code. So if you need any help debugging, feel free to post in the chat, because the most common issue is the Python version, I think. So yeah, the Python version is a big pain, but yeah, it's quite hard to solve. But we'll try our best to help you like via chat or like via like speech, I guess. But yes, if anyone has any issues online, just type in the chat, let us know. Right? And if you're done, you can just fill in the quiz and also the feedback. Okay, I'll continue helping the physical people. Right. No worries. Good job.
Yeah, so hi everyone. Yeah, so I think this is one of the benefit of being physical, is that we have allocated time and our manpower to also help out the physical participants as well. So if you are capable, you are able to join the workshop physically, then I think you'll gain a lot out of it. So do sign up physically next time. Thank you very much.
Emotion. Okay. For example, FPV or something.
Hello, is everyone online okay? I hope it's okay, I guess.
Wait, this is the cake.
I think you'll see the mouse.
Sell food. Sell food.
Bro. Anyway. Right. Wait, I was telling for like the past week, past week, like, what? You cool. point of going, but I don't know,
Hearing first class.
what? No, but I like you have advantage for a lot. It's like, is that on what? Like, is that on
Depending on the whatever question that you decided to go for.
side?
Very because there was one group that did it, right? Then they did the entire question one story, and then after the prof was like, okay, going to this you're doing tutorial to question two. Then now I want tutorial to question two. Then what?
Wait, but that the prof get us to do this job.
Yeah.
Wait, we get paid us what's in there?
See there.
Wait, what?
Yeah. Then she was like, guys, my back hurts, so I'm not gonna stand up to it. Then she just write like the very corner of the room.
Yeah, I want to be a prof, you know? Prof, I just feel like that's like, yeah, my skill teach. I get paid off.
This is tough.
It's master tough one. Wait, are you year two as well? Year three? Wait, how you guys moving? On Monday, like I scored people like coming maybe like a whole bunch of like category. Like you guys were standing at the board of fun.
Yeah.
And you're like, what's going
Like
on?
what's going on here? No comment. Let's go.
You felt like- you felt like- Yeah, right.
Oh, yeah. I think there's no like as in like
But I really
we got 2 or 3. So you know then you add back. Yeah. Okay.
Well, you need to email the top. So that's why you talk about.
So it's
I want to. For those online, it's really like 9 o'clock. But yeah, if you have any questions, you can feel free to ask. But other than that, we'll be ending the meeting. So thank you very much for coming, and guess we'll see you again next week. Okay. Bye bye.